All right, we can go ahead and get started. So far we've got, looks like 43 people. That's a great turnout. Before I welcome our guests, I'd like to invite those who have not already done so. Please subscribe to our YouTube channel. The link is in the chat right now, Magnimind Academy. We upload recorded sessions of these talks so you can watch them later. And you can also comment any questions on our YouTube live stream or just let us know about what you think about today's talk in the comment section. Now I'd like to welcome Subhan and his workshop on accelerated Python and GPUs. We really try to find speakers at Magnimind who can give workshops like these with a different information or a different perspective that you wouldn't necessarily get in a data science education program that goes along with the programs that we offer at Magnimind. These programs range from focusing on just one or two fundamental skills of data science, all the way to helping your entire career change into the industry. Our goal at Magnimind is impacting as many careers as we can, and this is just one way that we do so. Subhan joins us as the Senior Developer and Relations Manager at NVIDIA. In this role, Subhan focuses mainly on different aspects of consumer internet or just how to improve the consumer experience of NVIDIA. Before this, Ali's career includes stops at eBay as the Senior Product Manager, as well as Symantec and Insight. Graduating from UCLA with a BS in Civil Engineering, Ali went on to get his Master's and PhD in Civil and Environmental Engineering at Stanford University. We are very excited to have him. Please now give your full attention to Subhan Ali.
Great. Thanks, Thomas. Really appreciate the introduction and opportunity to speak with all of you today. Thank you to all of you for joining today, as I'm really excited to be here talking to you guys about Python on GPUs, and happy to share more and give insights in terms of what we're working on at NVIDIA and how to take advantage of it in your day-to-day workflow. So as things kind of stand today, there's a number of challenges that really are facing data scientists in their workflow. The first one is it's time consuming. So right now, we've all been there. We're working in our Jupyter Notebook. We're working in our pandas Dataframes and our scikit-learn. And the amount of time it often takes to actually load up your data frame and continue to do a model training can be significant. And so, you know, we've been there where you're sitting up at the end of the day and just leaving it there to run and come back in the morning. Hopefully it's done by then, right? So it's definitely a time-consuming process. Second of all, it's costly. So the money component of this sometimes isn't something that we think about at the individual data scientist level, but it actually does add up. And so this is definitely something to be aware of. And last, it's frustrating. And there's nothing worse than sitting there, being frustrated in your workflow, and being able to try to make the most of what you can with what you have. It's definitely difficult, and the pain is real. And at the end of the day, these are all problems that are they're independent problems as I'm describing them here, but they add up, and they add up on top of each other. And so the more time, the more money, the more frustration, the longer it takes to get your job done, plain and simple. And at the end of the day, as a data scientist, we want to be able to get to our insights as fast and as quickly as possible. For us at NVIDIA, we've actually had a great amount of success with end customers in terms of being able to GPU accelerate their data science workflow. On the left side, we worked with Oak Ridge National Labs, and we were actually able to GPU accelerate their XGBoost pipeline. And by doing this, they were able to see a 215 times speed up. So to make that clear, let's say it took them 215 hours, they could now do that workflow in 1 hour or minutes, whatever unit you want to use. But this means less waiting. The second one was we worked with a Fortune 1000 retail giant, and we were actually able to work with them to improve their forecasting model, which allowed them to much more effectively manage their inventory. And this resulted in a $300 million cost reduction for them. So basically, better results led to a significantly better cost performance for them. And then the third is we worked with also Fortune 1000 streaming media company, and they were actually able to save $1.5 million on their infrastructure. So this meant less spending on their IT and their overall infra. So what does the data science process look like? So the data science process, there are different ways that people look at this, but I've broken it down here in terms of the way that we're thinking about it. But first, obviously, you want to classify your problem, and you want to make sure you understand what problem is it that you're trying to solve. The second is actually acquiring your data and being able to put it into a format, into wherever it might be, your warehouse, your database, wherever it is, multiple places, and you want to be able to put it there. The third is you actually have to be able to process that data. We've all been there where one, you're just kind of doing the transformations, the normalization, and then also cleaning up the data. It's rare that you have data that is already be able to be used straight from the source. But you have to be able to actually to refine that data so that you can actually make use of it. The fourth is modeling the problem, and so what features can you extract, and then more importantly, what model can you use in order to predict on? So this is definitely a really important part, and here would be obviously a machine learning model, a deep learning model, potentially either way. And then second to last is validation and execution, making sure that our model is performing as we thought it should on data that it has not seen before. So we want to be able to make sure that we can do that. And then finally is deploying that model. So usually in inference where end customers would actually see the output of model predictions. So across all of this, the important thing here is if there's a slowdown in any one of these parts, the overall time for your cycle can be significant, and so you want to be able to remove any and or all of the bottlenecks at each of these stages. So a lot of you are probably familiar with this, what I'm showing here. So at the top, data prep, model training, visualization, this is well known. Dask, I'll get into this in a little bit. I won't actually get into it right now, but it is an important thing. But the blue squares are probably what you're most familiar with. So working in Python and Jupyter Notebook, we all use pandas data frames. Pandas is really well known and widespread. But there's two problems that you run into it when you get into a really big data set. One is the amount of time it actually takes to load the data frame. That is real and that does happen. And then the second part is how big that data frame can actually be. With pandas, both the pandas and scikit-learn, but you're fundamentally relying on CPU memory. And so whatever the in-memory limit is of that CPU, you're capped out by. So you can't go super large if you're sticking to pandas. Scikit-learn, similar problem, which is it's something that we all know. You can do your random forest, you can do your regressions, classifications, whatever it might be. But if you're trying to do a model training, again, you'll run into the same problem because of the underlying CPU architecture. And then the other ones are things that people may be familiar with as well. Graph analytics, obviously deep learning, PyTorch, TensorFlow, and then visualization are also all parts of it. But here, the important thing to underscore is this is all the Python that we know and love, and it's all easy to use as an end user. You just go ahead, spin up your Jupyter Notebook, install libraries, do your conda, pip install, whatever it is, and get these going, and then actually using them in your workflow. But once you get to really large data volumes, once you get to really long training times, you begin to feel the pain, and that's really the pain point that I want to provide a solution to you here with what I'm going to show next. So at NVIDIA, we have been working on really a overarching Python set of libraries that will help fix a lot of the problems that I just described. And broadly, we call this Rapids. And so Rapids, you can go ahead, you can install that by going to rapids.ai, and you can actually take advantage of GPUs in the exact environment that you want to be able to take advantage of it with. And so you can do this on your computer just by using Jupyter Notebook on your computer. You can do this in the cloud. All three clouds carry GPUs, and you can also do this in your on-prem deployments if that's where you want to do it. But to get back to the meat of this, As I talked about previously, so this the second one here, pre-processing, I was mentioning pandas. If you were to use a library that we have called cuDF or cuDataFrame, that's kind of a way that you could get around this problem. And then this third bar here, cuML, which is cu machine learning. And instead of using scikit-learn, you could get around the long training times that you have there. And then we also have the same thing for graph, cuGraph, and then cuStreams. You may be wondering why these all have cu in front of them. The reason for this is about, I think it was maybe 10 years ago or longer, NVIDIA invented a language called CUDA, C-U-D-A. And it's written really in lower level primitives around C, C++. And let's be real, I personally have never written in either of those languages. And most data scientists work in Python, SQL, so some work in R, obviously, but you want to be able to stay in what it is that you're doing. And so Rapids was really created so that we took care of that plumbing between the CUDA layer, the C, C++ layer, and the Python layer, so that you can just stay in Python. You don't ever have to think about CUDA. But we named each of the individual packages around CU. So cuDataFrame instead of pandas, cuML instead of scikit-learn. And the reason we did that is because we really want to be able to make it as familiar and as easy for you to actually take advantage of your workflow without having to redo your entire pipeline, your entire syntax, your entire code. All of this relies on this gray bar that I have at the bottom here, which is in GPU memory. So you're taking advantage now of GPU memory, and you're being able to actually go ahead and get off of the CPU. And then the other important thing here is all of this is underlined by Apache Arrow. Apache Arrow is a in-columnar memory format. It was created by Wes McKinney, who was the original creator of pandas. And it's really, the real focus of Apache Arrow is around you being able to take your data and move it to whatever framework, whatever package, whatever warehouse as easily and as effortlessly as possible without having to go ahead and do all these painful things, just moving data around. And so NVIDIA, we've bought into this as well as a number of other industry partners. But Apache Arrow, we really view as kind of the way to go and the way to move things forward into the future. So that's really the way that we're thinking about this and trying to drive this moving forward. What does this mean, though? What does this all equate to, truth be told? Well, it comes down to really, really, really fast performance and being able to do it as quickly and as cheaply as possible. So we're talking about going from hours to seconds. So on this graph on the right, the four top options are all using CPU nodes. And so the dark green is data load, the middle is data conversion, and the last is the ML part. Here we're talking about XGBoost. But like you're looking at here, which is 20 CPU nodes, and 20 CPU nodes it takes across the whole pipeline. We're talking about 8,700 seconds. So this comes out to roughly about 2.5 hours. Okay, and then as we increase the number of CPU nodes, we're able to get that all the way down to 3,000 seconds, which is about an hour. So you're talking about from 2.5 hours of 20 CPU nodes, you use 5 times the number of CPU nodes, you get it down to an hour. Okay, well, great. And this is all really expensive, by the way. So on the right side, I have TCO here. So we're going from $23 to $42 in order to get it down to an hour. And if you were to actually move this whole workflow over to Rapids, and you were to do this on our latest GPU architecture, which is the A100, we're talking about going from the fastest on a CPU, which is 1 hour, down to 2 minutes. And then on the TCO, we're going from $42 to $2. So just take a second to think about that. If you could take your workflow from anywhere from 2.5 hours to 1 hour and do that in 2 minutes instead, what does that mean you could do? How much more could you accomplish in a day, in an hour, instead of having to sit there and wait for your data to process or your model to train or whatever it might be? Like what more could you do with your day and your time? You could do a lot more. And I'll even talk about a little bit later specifically what we were able to do. And by the way, this is also using a 200 gigabyte CSV data set. So this is a very real data set in terms of something that you would come across. But what it comes down to, the bottom numbers, so 16100s provided more power than 100 CPU nodes. This is a 70 times faster performance than a similar CPU configuration. And this was a 20 times more cost effective than a similar CPU configuration. So this was better, faster, cheaper, plain and simple. As I talked about earlier, Ku data frame. So instead of using pandas, but it's very similar syntax, you can actually go ahead and use Ku data frame. And what does this really mean in terms of the end effect? So on the right side these are some very simple operations that I think many of us have done with pandas: merge, sort, group by, and this is speed up. So this is times faster. So that leftmost bar, 970, that means if it took you 970 seconds before, you can now do it in 1 second. Same thing with 500 seconds to 1 second. And the darker green bar is doing this on a 100 million row data set. And then the lighter green bar is doing it on a 10 million row data set. So what you're seeing here is that the bigger the data, the bigger the speed up. So bigger data sets benefit even more from this because of the parallel processing nature of the GPU, which lends itself really well to very, very large data sets. So across merge, sort, and group by, significant speed ups all around. So far I talked about data frames, and you can actually do the same thing with SQL. At NVIDIA, we've worked with a partner called Blazing SQL, and they've been really, really great. But basically what they allow you to do is Blazing SQL allows you to take advantage of running SQL queries on the cuDF data frame that you already have and you're holding in memory. And so it's really great. It works really well with Rapids, and it's actually built completely on top of Rapids. And you can actually go ahead, import your data in from S3 into GPU memory using Blazing SQL, and it's really beneficial. You can actually try a Blazing SQL notebook for free at this link here at the bottom, app.blazingsql.com. And so it works out really well. On the right side is what we're comparing. We're comparing Blazing SQL with Spark. And so what you'll see here is for a 3.8 gigabyte data set, we're going from 1,000 seconds down to a fraction of that. It looks like 100 seconds or less. And then for a 15.6 gigabyte data set, we're going from close to 3,000 seconds to way, way less. And so the speed ups here are really, really significant. For stream processing, there's a lot of streaming solutions out there for streaming data. Most of them are, probably related to Spark or Kafka. But the one common streaming solution for Python is the streams library. So what we were actually able to do is we were able to use the streams library, and we were able to use Rapids in order to do multiple or parallel stream processing at the same time. And so what this allows you to do is allows you to get a 25x speed up. And what you're seeing here in terms of the graph on the right is the overall TCO improvement. So on simple aggregations, you're getting a full 1x TCO, so it'd be half the cost. Complex aggregations are getting close to 4.5, so it'd be 20% of the cost. And then in a short time window, you're getting a 3x TCO improvement, so probably about 1/3 of the cost. But all across the board, if you can use Q streams, you can parallel process all of your data, and this allows you to go a lot faster. This is a specific implementation of cuDF for recommender systems. One of the problems that we've observed with recommender systems is that the data loading can become IO bound, and so being able to actually pipe the data into the recommender system effectively is really, really, really important. And so CSMV Tabular is something that we built in order to do this. What you'll see here on the right side is the leftmost bar is running Spark on CPU and then using PyTorch for the GPU training. And so you're seeing a solution that takes you close to 15,000 seconds. Next is what we go ahead and we do is we actually just go ahead and use CSMV Tabular for the ETL part, and you see a huge speed up. And that was on the V100, which is our older chip architecture. If you do this on the A100, which is our newer architecture that just came out, you get a further speed up. And then if you actually go ahead and instead of using PyTorch, you use huge-CTR, which is a GPU optimized recommender framework, then you actually get an even bigger boost in terms of whether you're using the DGX1 or the DGX A100. So it's definitely significant there. So in terms of, oh, sorry, I got my slides screwed up. Okay, yeah, so in terms of what I mentioned earlier, I mentioned Dask, and the key thing here with Dask is what is Dask? What does this mean? What does this really add up to? Dask is, so what I'm showing on the right side is, let's suppose I have a bunch of tweets, and the tweets go from January of 2016 up until May of 2016. So if I was trying to load this into a pandas data frame, all I could do is I can only load the tweets from February 2016 because they will fit into a single pandas data frame. So I'm limited by that. So if I wanted to actually go ahead and I wanted to load all of the data, all the tweets into memory at one time and distribute that across multiple CPUs and multiple GPUs, Dask would allow me to do that. So Dask does work with both CPUs and GPUs. And so in order to load all the tweets from January 2016 all the way up until May of 2016, I could use Dask, I could scale out across multiple CPUs and multiple GPUs and get all of the data into memory at one time. And so Dask is really user-friendly. It's very efficient. So basically it allows you to do a bigger data frame across rows or overall terabytes. It keeps you in Python, and it actually goes ahead and it takes care of all the backend scheduling, execution, decomposing into smaller data frames. You don't have to deal with any of that yourself. It takes care of that all on the back end. So it really does make your workflow significantly faster. So in terms of accelerated machine learning, we have Kumo, and this one here is, Kumo follows very similar scikit-learn methodology and support in terms of the specific algorithms that are supported, and I'll talk about those in a second. But here we're just using XGBoost, and similar story to what I showed earlier, but we're going from 20 to 100 CPU nodes, and then just doing the model training allows you to go to a minute and a half. So again, significantly faster. The algorithms that are supported here are pretty much all the ones that you're familiar with. So classification, regression, inference, pre-processing, clustering, time series. So your favorite random forest, logistic regressions, all those sorts of things are supported by Kumo, by the GPU accelerated scikit-learn. And then we do the same thing for graph analytics. So for the graph analytics, we go ahead and we have I'm no expert on graph, but if we're going from several CPU threads, 800 CPU threads that are taking 6,000 seconds, depending on how many GPUs we throw at the problem, we can go from 30 seconds to 1 second, so significantly faster. So there are a few questions that I'm seeing here. I'm going to go ahead and try to answer them as well as I can. So there's two questions that are around the Python code to run the IDEs on the GPUs in the laptop or in a Collab. So the quick answer to this question is yes, there is specific Python code, but it's pretty much follows the exact same syntax as pandas. So instead of doing an import pandas, you would do an import cuDF, and then I don't know the syntax off the top of my head, but and then in terms of the calls, when you're actually manipulating the data frame, it would be very similar to what you're using on pandas. So what I would recommend doing is on rapids.ai, our website, we actually have several example notebooks that walk you through how to do the exact same calls from pandas to cuDF. And so it's very clear. It would be much more efficient and accurate to actually look at that is the direction that I would point people in. And then just so you know, this presentation is being recorded and will be posted to the Magnimind YouTube channel afterwards in terms of the presentation content. And then the security about the data while using GPUs and caching on the cloud. I don't think I necessarily have a crystal clear answer to this question. What I will say is that you can run Rapids on-prem or in the cloud. And so if you're running Rapids on the cloud, most of the customers that I work with are generally on AWS or Google Cloud. And so they don't really run into security problems when it comes to that. I've seen a few kind of outlier scenarios when it comes to people having air-gapped environments, but that's not the vast majority of customers that I come across. And then the question around deep learning image processing. I don't think I have a crystal clear answer for this one. For NVIDIA, we have a lot of solutions when it comes to image processing. And I wouldn't, I think I'd be speaking out of my element if I was to say that this is the best solution that we offer. I know that there's a lot of work that we've done on the ResNet and image processing side, but that's probably not the scope of this talk or presentation, to be completely honest. And then there's a question. So to access the Rapids package, it is a GitHub repo. Go to rapids.ai. There's a GitHub link on there. I would go there. Rapids is actually an open source platform. NVIDIA is the largest contributor to it, but anybody can contribute to it. So it's completely open source. And then there is a question here around CPU performance measured on Intel or AMD or both CPU architecture. What configuration? What was the NVIDIA GPU model used for comparison? Great question. So I actually have all those numbers here. And in every slide that I showed, I think I actually called out what the exact configuration was. But just for this one, this is for cuDF versus over pandas over CPU. But on this one, we looked at NVIDIA Tesla V100 and we compared it to Intel Xeon CPU. I have some more call outs on every single slide here. So I would actually refer to that in terms of the details of where we actually did the analysis and what configuration. We've got a good amount of time left. What I'll actually do is I'll go walk through a kind of a case study that we did in terms of a case study that we did in terms of here at NVIDIA with a real problem that was very substantive, and using Rapids gave us a significant competitive advantage. Earlier this year, there was a Rexus challenge. So I think people have probably heard of Rexus, at least directly. But it's the Recommender System conference, and they had a challenge that was actually sponsored by Twitter. And the objective of this challenge was to actually analyze 200 million tweets and then predict what the user behavior was on those tweets. So could you develop a model that would actually allow you to do that? And that's kind of the way you can read more about the Rex's challenge at this link here on the slide. So in terms of the data set that was given, this is 121 million rows by 24 different features or columns. So each row was interaction between a tweet and a user. And so what you can actually see here is a bunch of different examples of what the features look like on this data set. And then and so all the ones that are not in the green box are the ones that were kind of given to us. And then at NVIDIA, we have a team of Kaggle grandmasters who competed in this competition. And they actually used a feature engineering process called target encoding, where they created new features from the features that they were given. And so I'm not an expert in target encoding by a long shot, but basically what they did was they created these new features and basically encoded the other features as a 0 or as a timestamp. So the outcome of this overall competition was basically we at NVIDIA were able to pretty much blow the competition away. And so pretty much across every single metric that you can look at here, but most importantly, the ones on the far right. NVIDIA, we came in at 133, second place came out 93, third place came out 90. But really, we were able to really take the cake on this one, do really, really, really well. So the question is, how do we do well? Why do we do well? What was the secret sauce that we employed here? And you can actually, our first place solution, you can access it on GitHub at this link, github.com/rapidsai/deep-learning/tree-main Rexis 2020. And this is where I'd go if you actually want to see the actual coded solution. But I'll talk through what the high points are, what we did here. So at the end of the day, we used an XGBoost model in order to solve this and come up with the most accurate predictions. So what we're looking at here is on the right side, kind of the code that we use in order to actually go ahead and import the XGBoost model, and on the left side, what were the actual metrics in terms of RCE that we were able to achieve here. But here's the real the thing that I underscore. The training machine learning pipeline that we use, obviously you train the data, you feature engineer, you model validate, and then you're actually able to predict. The thing that Rapids allowed us to do was it allowed us to do the feature engineering extremely quickly. And so this was really important because this allowed us to come up with new features very quickly. And then because we were able to come up with the new features and test what the feature importance was faster than anybody else could, we were able to actually do the prediction and then decrease the whole cycle timeline significantly. So this allowed us to get a lot more iterations in than would have been possible otherwise. And this was the real magic to what it is that we were doing. So in terms of the overall timeline, in terms of how much faster this got, so at the left side we're looking at CPU, and this is taking close to 3,600 seconds. And then on the second option, we just went to 1 GPU. And then because of this, we're able to get it down to 1,000 seconds. When we increase it to 4 GPUs, we were able to get it into a quarter of the time at 270 seconds. And then last, we were able to use a networking technology called ECX, which I'll talk a little bit more about. And this actually significantly increased the throughput between the GPU communication. There's multiple GPU communication, and this really allowed us to get additional acceleration in terms of what was going on. So we went from a CPU-based workflow that was 3,600 seconds, and if you use all the goodness, multi-GPU, ECX acceleration, we're able to get this into 2 minutes. So this is a significant time savings in this competition. Here, this is talking about when we went to multi-GPU, we were doing using DAS in order to do that with DAS Rapids QDF. And so what this allows you to do is, if you're looking at the right, we're looking at the V100s, and so we're able to pipe through significantly more data between all the V100s and the PCIe switches. And so this is really great. This means 4 times the GPU, 4 times faster, 4 times the amount of memory. So you're able to do this faster, you're able to do it at a higher memory rate, and again, just gets a lot faster. And then what we've got here is the calls that it took to do the Dask, and import that into the Python code. So importing Dask, and again, very simple calls that can be implemented. These are the calls that we use for Dask XG Boost. And so we get to 4 times GPU, again, 4 times faster, but relatively simple calls in terms of what we're able to go ahead and do. ECX acceleration, this is what I mentioned earlier, but what we're getting here is, just getting the 4 GPUs doesn't mean that the data communication between all the GPUs is faster. And when we actually go ahead and use ECX, we're able to increase the throughput of the data communication in order to allow full acceleration to be realized. So on the left side, we're, again, the simple calls here, and this is taking care of, this is just implementing the ECX and getting us to kind of where we need to go. And then on the right side, so you're getting 4 times GPU, but because you implement ECX, you're able to increase the throughput. So we're getting 8x faster. So again, this really helps get the full acceleration out of the total pipeline. So this is the story here. Really is we're going from 11 hours to 2 minutes, and so across the board, this is a really fast speed up that we saw, and you're seeing this across the entire thing. The important thing is that I mentioned earlier. The blue bar is target encoding, and so you're seeing target encoding was a specific feature engineering task that we used. So the blue bar is dropping significantly, and so what that means is, this speed up in feature engineering, this really allowed us to be able to speed up the entire pipeline to go from 11 hours all the way down to 2 minutes. Again, this is the overall results that we saw. Again, we blew up the competition out of the water, yeah. So I'll go back to the questions. Let's see. Security, I mentioned that one. Yeah, so you can go to rapids.ai. That has quite a bit. And then, is there any comparison in terms of time and number of CPUs used on cloud platform or a single server? That's a great question. So the answer to that question is yes, we do have those comparisons. What I generally tend to find is people, if they're asking this question, they want to see it on their specific cloud. And then, like I said, I work with mostly customers that do Google Cloud or AWS. And so I don't have those numbers off here, but I'm happy to provide those numbers if there's interest. Target encoding is basically a feature engineering feature where you create new feature engineering method where you create new features from existing features. So I didn't actually go into the nitty-gritty details here because I'm by no means an expert in target encoding, but at a high level, that's what it is. I can point you actually to a pretty detailed blog post that we created around the specific target encoding that we did for this competition. So should I have a distributed computing knowledge to deal with rapids, and what about interfacing with TensorFlow and PyTorch? So you don't really need a distributed, you don't really need a distributed computing in-depth knowledge. Our recommended distributed computing plugin for this is Dask, which will allow you to actually take advantage of multi-node, multi-GPU, and just scale up. We've been able to, using Dask, get to like 10 terabyte data sets all in memory. So you're good there. With TensorFlow and PyTorch, yes, Rapids does interface with TensorFlow and PyTorch. Depending on what problem it is that you're working with, I can go all the way back. kind of show that slide specifically. But yes, we do interface with TensorFlow and PyTorch. I don't have the details on that, but I can provide more offline. And then let's see. Yeah, so in terms of the cloud performance number, I would go to rapids.ai/HPO. That should have specific cloud numbers for Rapids on cloud. Is DAS developed by NVIDIA? Great question. The answer to that question is no, it is not. Dask is actually, there's a Matthew Rockland developed it, and he was at Anaconda, and he's still the maintainer of it, and he started an independent company called Coiled. But Dask is kind of similar in a lot of ways to Array, which is another very popular Python distributing framework. No, it's not developed by NVIDIA. We have several Dask contributors though at NVIDIA. And yeah, so, and then there's another question here. How can we build a portfolio to show that we really know how to use Rapids or CUDA for GPU usage? Can you give some guidelines? It's a good question. I mean, ideally, if you're using Rapids, you're not coding in CUDA, truth be told. You know, I think the place I would point you to is our Rapids GitHub page, which is rapids.ai, and then there's a GitHub link on the site. So I would definitely go there to check out, notebooks that we have in terms of problems that we've solved. There's a lot of examples out there of problems that people have solved with Rapids, but I would really, the best advice I would give is Rapids is a tool, and it's the same tool that most people use with pandas or scikit-learn. And so what I would recommend doing is, any problem that you solve one of those, you can solve it with Rapids. And so, yeah, but the thing is that Rapids will allow you to do it with larger data sets and significantly faster. And so I'd really recommend just solving the same problem, but doing it with the GPU and doing it with Rapids and see what the benefit is that you can get. That's really what I'd recommend there. Let's see, I've got some more questions. Should one use CUDA or Rapids for ML application? So yes, you can. I mean, again, if you're using Rapids, you're not coding in CUDA. And so for Rapids, specifically, you'd be using the middle library here, QML, Ku machine learning. And so yes, you easily can. It would be a big benefit. As both use NVIDIA GPUs, right? So yes, all this is built upon NVIDIA GPUs. So yeah. Another question that I find sometimes is people will ask, is there a specific type of GPU that you need to use? The answer is no. Pretty much any NVIDIA GPU will work, including a lot of the customer-facing gaming cards. Those will work too. So like we've been releasing the 3060, 3080 graphics cards. Those can take advantage of Rapids as well. So you're not really constrained to really any GPU. The only problem is if you go to like much significantly older architectures, we may not support that. But there's not that many of those out there still. So.
All right, is that it for questions?
There's one last one around for using the
Gotcha.
cloud platform already. How can we get NVIDIA GPUs and Rapids set up there? Yeah, so I'd recommend going to rapids.ai/HPO or rapids.ai/cloud, I think. But yes, you can get Rapids set up on a cloud platform very easily. We work with customers that are using it on AWS, Azure, and GCP all the time.
Awesome. Thank you so much, Subhan, for. What was that one more?
Will it be billed separately?
Yeah.
Yeah. I mean, the key question there is what are the instances that you're using? So if you're using CPU instances versus GPU instances, you'll be billed a different rate for each of those. What we generally come across though is that when people are using GPU instances, it's very overall the amount of time it takes you is significantly lower, so the total cost will be significantly lower for you. And there was one other question. I think it was will Rapids run without GPUs? No, it will not. It has to run on GPU. So the code will fail if you try to run it without GPU.
All right. Thank you so much, Subhan, for giving us this talk today. I don't mean to take the floor away from you. It's we still have a little longer if you need to go longer, but
I'm happy to stick around and answer any questions if anyone has.
Yeah,
sure. There's another one. Is it possible to run this for small data sets? Yes, it's possible to run it for very small data sets. The benefits really kick in when they get to larger sizes. But yes, very, very, very possible to run for small data sets. No, I don't think that there's any effects when it's run on a small data set. It'll still be very accurate. Yes, I'm happy to share this deck. I will share this with the organizers, and we can go ahead and send this out to all of you.
That reminds me one more thing. If you could send me the presentation as well. A lot of times I get reach outs after these are over asking for the slides. I'll make sure to contact you after that, though.
Yes, I will share this with you.
Awesome. Thank you. Okay.
Oh, somebody asked, how can we connect with you for my company needs? Yes, I'm happy to help anybody who's interested. Feel free to connect with me on LinkedIn, or I can find my email. It's my first name, subhan@nvidia.com, and I can definitely help point you in the right direction if there are questions as needed. And then there's more questions here. Is there an API for image processing like OpenCV? I believe there is. I don't actually have the best answer for this, should be told. But yeah, I mean, there's a lot of image work, computer vision work that we do at NVIDIA, and I'm unfortunately not the expert on that exact topic. There's another one on can be used in streaming data with GPU. GPU can be used in ETL processes. The answer to this question is yes, it can. And I actually covered this, I think, in my talk. Let's see if I can go to that slide. But yeah, you can use. Come on. Yeah. So right here, this is for streaming data. You can use QStreams, which is built upon the open source streams library, and this will actually allow you to take advantage of streaming data. So basically, it allows you to have multiple data processing streams at the same time. Can Rapids run on Collab? This is a good question. It can. Answer is yes. Collab is a very common, Google environment that people use. The problem with Collab that we found, unfortunately, is that Collab is free, so you're never guaranteed a specific type of GPU, so yeah, it's kind of hit and miss. Sometimes we'll get a great GPU, sometimes we'll get a very bad GPU. So if you want to be able to guarantee the GPU that you get, you really need to you actually need to pay Google Cloud for that. So I think oh, okay, there's another question around the answer to the TPU question. No, it cannot run TPU. And then so what are the use cases where rapids and GPUs are most recommended, not just the data size? Yeah, I mean, that's an interesting question. I'd say, depends on what you mean by use case. In terms of what I focus on is the data science operation that someone's doing. Sorting, cleaning data, doing the model training, whatever it might be. I work with end customers. I work with end customers. So what I find myself doing a lot of is fraud detection, logistics, personalization, recommender systems, anything like that. So I mean, Rapids is a tool. How you use that tool can vary widely, but it can be really used significantly across the board. There's a question around RCE and reverse cross entropy. I'm not going to pretend to be an expert on this or to speak at length about this because I wasn't the Cavalry Grandmaster competing in this competition. I'd refer you to we have some blog posts around this. So if you were to search for Rexus 2020 Rapids, you'll find a much more detailed walkthrough of why they chose what they did, but I'm not the expert on that one. There's a question around can these be used in edge devices with GPUs? That's an interesting question. I think the answer to that is yes, it can. I don't think many people are trying to do this, but I think it can be done. Rapids can be used with R or any other language like Scala. Okay, good question. No, it cannot. It can only be used with Python. We've gotten a lot of questions around R, and so we with R, we are not yet supporting it, but that's definitely been a big question. Scala, interesting question. Yes, Rapids can be containerized. Yes, it can. You can download the containers on anywhere that you'd really like, and Rapids.ai will point you in that direction. Scala, Scala is by and large used with Spark, is what I find, and NVIDIA does have GPU accelerated streaming solutions GPU accelerated solutions for Spark that I did not go into here today. We have announced it, but I don't know if it can be used with Scala or not. But yes, it can be used in Docker or Kubernetes for containers. And then let's see, any other? There is a question here from the Collab. So when we switch runtime to GPU in Collab, does it mean we are running in GPU, or do we still need to import the Rapids library? Oh, great question. So when you switch from runtime to GPU in Collab, all that's happening is it's basically using the GPU. Now it means that the Collab instance is GPU aware. So it knows that the GPU is there, but it doesn't actually mean it's using the GPU. So you still need to import the Rapids library. So in any environment, you would actually need to explicitly call Rapids, because if you don't do that, then it's just going to fall back to CPU and you won't get the acceleration. So even if the GPU is there, you actually have to use Rapids in order to get the acceleration and take advantage of the GPU. And then what else is coming up here? Python has R libraries, so it could work with R if invoked via Python library, right? That is a great question. I have never gotten this question before. I don't know the answer for sure, but if it's executing inside Python, it should work. I don't know if there's a dependency that Rapids would need to use in order to do this. So I don't know the answer to that question, but it's a great question. I've never gotten this question before, and I will find out the answer to that. Containerization possible in Rapids. I'm not 100% sure about the answer to that either. but yeah.
All right. Well, I feel like you've definitely set the record for our talk so far. Is questions answered. Thank you so much for answering all these this way. And thank you everyone for attending this workshop, and of course Subhan for your time. We hold these talks to inspire people to keep furthering their learning, and if you've come here, you've done that today. If you haven't already, please make sure to subscribe to our YouTube channel and comment what you thought about today's meetup or what you think about our online Zoom format. Also, please join us for our next scheduled meetup, which is going to be on December 9th. It's called Data Science. I've just lost it. Data Science and Mental Health Opportunities and Advancements. Thank you, everyone, and have a great night. Great rest of your day.